Hi everyone, today we'll be talking about ions and ionic compounds. By the end of this video, you should be able to explain what ions are, how they are related to atoms, and how they form. You should also be able to explain how ions come together to form an ionic compound held together by ionic bonds. You should be able to explain what ionic bonds are. You should also be able to describe and explain the properties of ionic compounds. To understand what ions are, let's first start by understanding what atoms are. Atoms are the smallest divisible unit of matter that has the properties of an element. That is to say that it is the smallest piece of matter that behaves like an element. By definition, atoms are electrically neutral, and that's because atoms are made of subatomic particles, and two of them, the protons and the electrons, carry the exact equal charges. An atom always has the same number of protons and electrons. For example, a helium atom carries 2 protons and 2 electrons. So it has a total of 2 positive charges and 2 negative charges, giving it a net charge of 0. So now we know what atoms are. What about ions? Ions are atoms with electrical charges due to unequal number of protons and electrons. The unequal number of protons and electrons arise through the loss or gain of electrons. For example, if an atom were to lose one electron, recall that electrons carry the negative charges. So if it loses one electron, it would have one negative charge fewer than positive charges, transforming the atom into a positive ion with a positive 1 charge. On the other hand, if it were to gain one electron, now it has one negative charge more than positive charge, transforming it into an ion with a negative 1 charge. Now at this point, you might wonder, why can't ions form through the loss or gain of protons instead of electrons? There are two main reasons for this, and it's to do with the properties of protons and electrons. The main reason has to do with the location of these subatomic particles. Within an atom, a proton is located in the nucleus, which is deep at the center of the atom, which is much more difficult to access. Whereas the electrons are located within the electron shells, which is on the surface of the atom, which is much more easy to reach. Also, a proton is much heavier than an electron, almost 2,000 times heavier. Both of these factors put together means that it is much easier to ionize an atom. Ionize is the process by which ions are formed. It is much easier to ionize an atom by moving electrons than by moving protons. So now we know what atoms are and how they are turned into ions. Let's talk about one type of ion, the positive ions. Positive ions are predominantly metals. Metals are the elements that starts on the left-hand side of the periodic table. Metal elements have a tendency to ionize by losing electrons rather than gaining electrons. Some examples of positive ions are sodium, lithium, copper, iron, magnesium, and zinc. This is of course a non-exhaustive list. There are many more positive ions than this. While positive ions are predominantly metals, negative ions are, perhaps a bit predictably, predominantly non-metals. Non-metal elements have a tendency to ionize by gaining electrons rather than by losing electrons. Some examples of well-known negative ions are the ions from group 7 or group 17 elements, the halogens: fluorine, chlorine, bromine, and iodine, which ionizes by gaining one electron to form fluoride, chloride, bromide, and iodide, respectively. So at this point, you should be able to briefly explain how ions form. Recall that ions form when an atom loses or gains electrons. But atoms are non-living things, so what motivates the atom to lose or gain electrons? Well, it turns out that atoms are motivated by the pursuit of energetic stability. Without going into the details, an atom with an incomplete valence electron shell is less energetically stable. What is a valence electron shell? A valence electron shell is the outermost electron shell of an atom. It is the electron shell that is furthest away from the atomic nucleus. If that electron shell is not completely filled, then the atom is less stable compared to when the valence electron shell is completely filled. There are two ways to completely fill a valence electron shell. One way is to gain electrons to fill up the remaining spaces. Another way is to lose all of the existing electrons in the valence shell so that the electron shell underneath will become the new valence electron shell. Which way is used depends largely on how many valence electrons does the atom originally have. In the case of the formation of positive ions, recall that they are predominantly metals. Metals have relatively small number of valence electrons. For example, sodium atom has an electronic configuration of 281. An electronic configuration is a written representation of the arrangement of electrons throughout the electron shells of an atom. 281 simply means that a sodium atom has 2 electrons in its first shell, 8 electrons in its second shell, and 1 electron in its third and also valence shell. A sodium atom can take a maximum of 8 electrons in its valence shell. So as you can see, it is a long way from having its valence shell being completely filled up. Same goes for magnesium with 2 valence electrons, aluminium with 3, copper with 1, zinc with 2, and iron with 2. All of the elements shown here can take at least 8 electrons in their valence shell. So all of them are a long way from having completely filled valence electron shells. So there are 2 ways they can fill this up. Let's use sodium as an example. For sodium to have a full valence electron shell, it can either lose its 1 valence electron shell so that its second valence electron shell would now become its new valence electron shell, transforming it into a sodium positive 1 ion with an electronic configuration of 2,8 with a complete valence electron shell. Or it can also steal 7 electrons from the surroundings to be put into its existing valence electron shell, transforming it into a sodium 7 minus ion. Now it also has a complete valence electron shell. However, under standard conditions, the second scenario will never happen. And one of the reasons why this would never happen is that it takes so much more energy to gain 7 electrons than it would otherwise need to lose the 1 electron that the sodium atom already has. And in fact, this is true for the majority of metal elements. For most metals, much less energy is required under standard conditions for them to achieve a full valence electron shell by losing their existing valence electrons rather than by gaining electrons to fill up their valence electron shell. So we have seen how positive ions are formed and why they are predominantly metals. What about negative ions? Negative ions are predominantly nonmetals because nonmetal elements have a relatively large number of valence electrons. For example, fluorine has 7 valence electrons. The maximum capacity is 8, so it's just 1 electron short of having a fully filled valence electron shell. Same goes for chlorine and oxygen, which is just 2 electrons short of having a fully filled valence electron shell. So how would non-metal elements achieve a full valence electron shell? Let's use chlorine as an example. For chlorine, to have a full valence electron shell, it can either lose all 7 of its valence electrons so that its second electron shell would now become the new valence electron shell, transforming into a chlorine 7 positive ion with an electronic configuration of 2,8. Or it can take the easier route and just gain 1 electron from the surrounding and fill up its existing valence electron shell, becoming a chloride ion with an electronic configuration of 2,8,8. Under standard conditions, only the second scenario will ever happen because it takes so much more energy to lose 7 electrons than is needed to gain 1 electron. For the majority of non-metal elements under standard conditions, much less energy is required for them to achieve a full valence electron shell by gaining electrons rather than by losing electrons. So at this point, we have explained what atoms are, how they are transformed into ions through the loss or gain of electrons, and we have seen how positive and negative ions are formed. But how do these ions come together to form a compound, the ionic compound, and why are they held together by the ionic bond? When a metal and a non-metal atom are close together under the right conditions, such as a sodium atom and a chlorine atom, the sodium atom in this example will lose its 1 valence electron to the chlorine atom. This transforms the sodium atom into a sodium ion with a positive 1 charge and the chlorine atom into a chloride ion with a -1 charge. Note that the two ions have opposite charges, and opposite charges attract. The opposite charges of the two ions is what's holding them together, and the forces of attraction between these two oppositely charged ions is what's known as the ionic bond. So the ionic bond is defined as strong electrostatic forces of attraction between oppositely charged ions. An ionic compound is simply chemical compounds held together by ionic bonds. Within an ionic compound, ions are arranged in a lattice structure. A lattice is a solid crystal with a regular repeating arrangement of atoms. Ionic compounds have their ions arranged in lattices. Different ionic compounds may form different types of lattice structures. For example, a sodium chloride lattice looks like this. A key property of ionic lattices is that ions of the same charges are never directly next to each other. And that's because same charges will repel each other, and this would tear the ionic crystal apart. And that's the reason why ionic crystals are brittle. This is a unit cell of a sodium chloride crystal. A unit cell is the repeating unit of a lattice. This means that a large sodium chloride crystal is made up of many repeating units of this. So now we understand how ionic compounds form and how the ions are arranged within the compound. What are some of the properties of ionic compounds? We're going to discuss this in terms of hardness, which is a measure of the amount of force needed to cause a permanent change in shape of a substance. In this case, is the ionic compound. Solubility, which is a measure of how much of a substance in terms of mass can dissolve in a solvent at a certain temperature. Volatility, usually measured in terms of melting and boiling points, which is a measure of how much heat energy is needed for a substance, the ionic compound, to transition from a lower energy state of matter, such as solids, to a higher energy state of matter, such as liquids or gas. And also electrical conductivity, which is a measure of how well a substance carries electrical charges. Let's start with hardness. Hardness is a measure of how much force is needed to cause a permanent change in shape. In order to change the shape of an ionic compound, or just any substance for that matter, the ions must move relative to each other. But what's preventing the ions from moving relative to each other? What's preventing this ionic compound from being deformed? Well, it's the ionic bonds. Ionic bonds is a class of strong chemical bonds. The strong attractive forces of ionic bonds prevents the ions from moving relative to each other. So the more force is needed to change the shape of a substance, the harder the substance is. So are ionic compounds hard? Yes, that's because ionic bonds are strong chemical bonds. Since they are strong, a lot of force will be needed to break them. Therefore, most ionic compounds are hard, but brittle. That is to say that when you successfully change the shape, ionic compounds tend to fracture or break. And that's because when you change the shape of an ionic compound, you are forcing ions with the same charges to be adjacent to each other. And recall that ions of the same charges repel each other. And that's why ionic compounds are hard but brittle. Solubility is measured in terms of how much of the substance can dissolve in a solvent, in this case water, at a certain temperature. So what affects solubility of a substance? It largely depends on how favorably does the molecules of a solute, in this case is the ionic compounds, interacts with the molecules of a solvent, in this case it's water. Water molecule has a property known as polar, and that is to say that it has an unequal distribution of charges. Water molecules are electrically neutral, but the positive and negative charges within a water molecule are not distributed evenly, and this is known as being polar. To interact favorably with polar molecules, it helps to have electrical charges. And what has electrical charges? Ions. For that reason, most ionic compounds are highly soluble in water, or at least partly soluble in water. Let's better understand this with a diagram. Ionic compounds, shown here with positive and negative charges, note that the oppositely charged ions are always adjacent to each other, and the ones with the same charges are never directly touching each other. Water molecule is polar, and a brief explanation of why is the oxygen atom of water is much stronger in terms of its ability to draw electrons compared to the hydrogen atoms. And for that reason, the electrons within a water molecule is pulled closer to the oxygen atom and away from the hydrogen atoms. So the hydrogen atoms, which are a bit lacking of electrons, would have a partial positive charge, whereas the oxygen atom, which has a larger concentration of electrons, would have a partial negative charge. When you add ionic compound to water, the hydrogen atoms where the partial positive charges are concentrated would interact favorably with your negative ions, whereas the oxygen atoms of water where the partial negative charges are would interact favorably with the positive ions. And that's why most ionic compounds can dissolve reasonably well in water. So something that is not ionic and non-polar would have trouble dissolving in water, and that's because they have no charges to interact favorably with the polar water molecules. For that reason, they would be excluded by the water molecules, therefore they are not able to dissolve well. This will include things like oil or plastic. The volatility of ionic compounds is strongly correlated with its hardness. A substance that is very hard tends to have high melting and boiling points. A substance that is very hard tends to be difficult to melt as well. And that's because for something to melt or boil, the strong attractive forces, the ionic bonds, needs to be overcome by the heat energy that is supplied to it. And since ionic bonds are strong, a lot of heat energy is needed to break them. For this reason, ionic compounds have a fairly high melting and boiling points. Right? So a lot of heat energy is needed to melt a solid ionic compound or to change it into gas. Lastly, electrical conductivity. Electrical conductivity can be thought of as how well a substance conducts electrical current, which is the movement of electrical charges from one point to another. What property would a substance need to move electrical charges? For one, it would need to have electrical charge carriers. Examples of electrical charge carriers are ions or free-moving electrons. In the case of metals such as copper or aluminium, they are conductors of electricity because metals have free-moving electrons. So when a potential difference or voltage is applied across the metal, the free-moving electrons can move, and that's what an electrical current is. But ionic compounds do not have free-moving electrons, but they do have ions. However, just having electrical charge carriers alone is not enough. The electrical charge carriers must also be mobile. That's because when a potential difference is applied across the substance, the electrical charge carriers must be able to move. When ionic compound is in its solid state, the ions are not free to move. When it is in liquid state, and this can be achieved either by melting it or by dissolving it in water, the ions become mobile. For this reason, ionic compounds are electrical insulators when they are solids, and when they become liquids either by melting or by dissolving it in water, they become electrical conductors. That is to say, a solid piece of salt cannot conduct electricity, but if you were to melt it or if you were to dissolve it in water, then it can conduct electricity. This is the end of today's video. If you have found it to be helpful, please hit like and subscribe. Thank you very much for watching.